Let's get started. Actually, before I begin, are there any questions about anything? Today we're going to continue on this fully quantum crypto theme that we started last week. Right, so this is the setting of cryptography where both the good guys and the bad guys all have quantum computers, and we all want to do some sort of crypto by sending quantum information to and from each other. In today's lecture, we're going to talk about quantum pseudorandomness and its applications. We probably won't get to its applications. That'll probably be next week, but that's where we're going. And in this particular lecture, it's going to be a mix of classical and quantum crypto, because we're going to build upon concepts and notions from classical cryptography. So we're going to talk about something called quantum pseudorandom states. This is a quantum analog of a pseudorandom generator, or a PRG. Pseudorandom generators are something from classical cryptography, so let's review that. Not everyone here is taking a crypto class, so it'll be good to just go over that really quickly.
Right.
Yeah.
So we just didn't
Oh, the order.
yeah.
Oh, yeah.
We can decide on it later.
Oh,
Right?
no.
Okay. When you see scribes, you have a template or something, right?
Yeah, template. You have to write
I
extra
have
content.
to write myself,
Yeah.
but it is recorded, right?
Yeah, but
So
you guys have to
on.
decide first half or second
Yeah,
half.
sure. We can do it later.
Yeah,
That's fine.
Yeah. Some sort of agreement protocol. Okay, cool. So what's a PRG? Just in pictures, at first in pictures, it's some box, G, that stands for generator. And the input to this box is some string K. Say it's an n-bit string. We call this input string a seed. It's a seed randomness to this generator. And it outputs a string that's supposed to be longer than n bits. So we'll call the output of this y. It's m bits long, and this is the output of the generator. And we're going to assume that m is greater than n. And the property of this PRG that we want is that if we feed in a uniformly random string k to this box, it outputs a string that's going to look uniformly random to all observers that run in polynomial time. Now I'm feeling self-conscious because now Tal's in the
No, but I know nothing about quantum.
so if I get something wrong, let me know.
Good combo.
Yeah, so we want that the output is distinguishable from random from the point of view of any time observed. So first of all, so G here is, it's a box here, but we're thinking of it as a deterministic function. Okay? It's just going to map strings to strings. And here you feed in a uniformly random n-bit string. And the first thing is the output cannot be uniformly random over n bits, right? Just as a sanity check, anyone see why? What is the reason why it cannot be uniform over n bits?
Most strings have probability zero here.
Exactly. So basically, the input space is smaller than the output space, right? So for mapping, you cannot cover all of the output space, right? although that's what the uniform distribution over the output space is supposed to be. Despite that, a pseudorandom generator has a property that if you give the output of this generator to another person, and that person doesn't have that much time to try to think things through, they cannot tell the difference between whether this was the output of the generator or whether this was drawn uniformly from the output space. So let's make this a little more formal. So do I have enough space? Let's say I do. Definition is that G, which is a function from n bits to m bits, is an PRG if it's all the time computable, meaning that there's some algorithm that doesn't take too long and it can compute this function. And okay, I think I'm going to run out of space, but for all only time distinguishers, D we're going to look at two probabilities. One is that we're first going to sample the input, an input seed from the uniform distribution on n bits. That's what I mean from k twiddle u sub n. And this distinguisher, this is an algorithm. Okay, so it's some algorithm that runs in polynomial time, and it gets the output of the generator on input k. So this distinguisher is going to output 0 or 1, right? So here we're looking at the probability over the choice of k, the input, that is going to output 1. And we're going to compare this with the probability that if this distinguisher gets not the output of the generator, but a uniformly random m-bit string, and it gets y instead, the probability that it outputs 1. The difference between these two probabilities is going to be some very small quantity that we call negligible. Okay, so negligible has some precise definition, but for now, just think of it as some vanishingly small quantity that goes to 0 very, very quickly. Okay, so that's the definition of a pseudorandom generator. There's technically, this is not quite it. Like you have to talk about sort of a family of different functions, but let's just keep it this way to make things simple. So let's just get a feeling for what this definition is saying. A distinguisher is just some algorithm, and we say that the algorithm has to run in a small amount of time. And think of the distinguisher as it gets an m-bit string as input, and is trying to decide, do I think that the string came from the generator or is it a uniformly random string? And this absolute value is saying that it really cannot tell the difference for any polynomial time distribution. So that's why we call it pseudorandom. The output's not truly random, but it looks random to any efficient algorithm. Okay, so that's the definition, and let's make a couple observations about it. And then we'll kind of repeat this for the quantum case. So the first observation is that in order for this definition to make sense, this polynomial time restriction on the distinguisher is necessary. So time restriction of the distinguisher D is necessary. So if we allow the distinguisher unlimited time, then there's no such thing as a pseudorandom generator. So why is that the case? Not you. Yeah, Rocky?
I'm in Tall's class, so maybe this is cheating, but you could just try running the generator for all 2 to the n strings. And then if the output that you were given was one of those possible outputs, you predict that it was from the generator.
Exactly. So if you allow the distinguisher unlimited time, this distinguisher could just memorize all the possible outputs of G and just say, is Y in that set of outputs or is it not? Then you can distinguish with probability at least a half, right? Because if you look at the space of outputs of all n-bit strings, the output set of the generator is at most size half. So yeah, so there's no, you need some sort of time restriction. So that's observation number 1. Another observation, this is closely related, is that many of us think or hope that pseudorandom generators exist, but we don't know for sure. If you show that a pseudorandom generator exists, then you've actually proven that P is not equal to NP. So you get $1 million. It's not that much these days, but still.
I'm sure you can get more.
Yep.
If you prove that P is not equal to NP.
Sponsorship.
I'm sure you'll be set.
Okay, so that's, so you know, it's not so easy to show that these things exist. People do believe them, or they hope that they exist, because virtually all cryptography relies on the existence of pseudorandom generators. In fact, you can prove that if you have some non-trivial crypto system, okay, so I'm being vague what I mean by crypto system here, then essentially no matter what crypto system you invent, it inevitably implies the existence of a PRD. So
You referring to equivalent to one-way functions and PRG?
yeah, okay. All classical crypto implies existence of PRGs. Okay, so by virtually, I mean, there's a couple cases when this doesn't quite apply, but essentially for anything that, you know, encryption or commitments or homomorphic encryption, you name it, if you have such a scheme, it implies somewhere in your scheme, you must be using a PRG, even if you didn't realize it. So pseudorandom generators are necessary. A couple other things, another observation. So the difference between the output length and the input length, we can call it the stretch, right? Because you're stretching n bits to m bits. And in the context of crypto, the stretch, which is, you know, the difference between n minus n, can be any polynomial. So in other words, it's not so important what m is. Like as long as you get, if you're able to build a pseudorandom generator that stretches n bits to n plus 1 bits, then there are ways to bootstrap that into getting as many output bits as you want as pseudorandom. So that's why people don't really specify what the output is, how long the output is. And, the final note about this is that here, this distinguisher, I said it's an algorithm. What kind of algorithm? In classical crypto, people talk about polynomial time classical algorithms. It also makes sense to say your generator, which is this deterministic function, also fools any polynomial time quantum algorithm. So in this context of post-quantum cryptography, which we talked about last time. So in PQC, we assume D can be quantum. And this only makes your definition stronger. It's saying that even if you have a quantum computer, as long as the quantum computer only runs in polynomial time, you cannot distinguish the output of the generator from uniform. Does the concept make sense to people? Okay. So this is the classical definition. And this pseudorandom states is really kind of an analog of this. So we're going to mirror a lot of these pieces, but in the quantum setting. So pseudorandom states. So I'm going to draw a picture first. So pseudorandom state, I'm going to abbreviate it by PRS. So it's another box. We're also going to call it G. It takes in as input a classical string, just as before. It's n bits. This is called the seed. But the output now is going to be a quantum state. So I'm going to call it psi sub k. This is a qubit state. And the property that we want from these states is that copies of psi sub k are indistinguishable from Haar random states. So remember, we had a couple lectures about Haar random states, and now all of this is going to come back. And this is indistinguishable from the point of view of an algorithm that doesn't have that much time. So from time. So we're going to just modify the definition of a PRG appropriately to get the notion of a pseudorandom state. Let me fix this. So the definition here, up here F. So G mapping n bits to a set of pure states on m qubits is a pseudo-random state generator. Say it's a PRS generator. If it can be computed in polynomial time by some quantum algorithm. And for all t is a number, that's polynomial in n. All distinguishers, polynomial time distinguishers, d. We're going to have a similar, difference of absolute values, but now the inputs will be quantum. So in one case, we have the probability that if you sample a random key that's n bits long, you give the distinguisher the output of the generator, but not just the output of the generator, it can also be duplicated a bunch of times. So the distinguisher can get t copies of the output of the generator. That's one case. And it's trying to distinguish between this and t copies of a Haar random state. So it's called theta, a state sample from the Haar measure. We can't tell the difference. So
What's the quantification on T? For all t?
for all polynomial t.
All polynomial.
So a t can be 1, it can be 2, it can be up to any poly n you like. No matter how many copies you get, as long as it's not, an exponential number of copies. Then this distinguisher, can't tell the difference between random and something that's the output of this generator. Definition makes sense? Yeah.
Maybe this is nitpicky, but do you need the restriction that t is poly n if your distinguisher also has to run in polynomial time?
I guess it matters how you define polynomial time, like in the length of the input or poly n. So you're right. If I'm saying distinguishers that run in poly little n time, then necessarily, like, if you give it extra copies, it doesn't even have time to process it.
Okay,
Yeah.
there's not some, yeah, I just make sure that I'm not missing some.
Yeah. All right, so let's go through similar observations to what we made before. It looks mostly the same, right? Except we now output a quantum state. But there's a couple of differences. One is that we have this number of copies t that didn't show up before. And this is a quantum feature, right? So let's talk about that first. So role of t. And this is an important part of the definition because of the no cloning.
G of, no,
Oh, yeah,
no, yeah.
So psi, I'm
okay,
using
yeah,
psi k to
yeah,
be
okay.
g on output.
Sure, yeah.
So
Yeah, okay.
that makes sense. So it's important. So no cloning. The reason it's important is because imagine we didn't have this number of copies thing. We just said, if you're given one copy of the output of G, you cannot distinguish it from a random state. That could be the case, but that's not very interesting because maybe if you then give 2 copies of the state, it suddenly becomes distinguishable. So in quantum, it's possible to have 2 ensembles of states. So let's say the ensemble is, I'm going to pick psi1 from ensemble E1 and psi2 from ensemble E2, such that psi1 is indistinguishable from psi2. So E1 and E2 are like collections of states. You pick one at random and you hand it to someone, right? So they're getting a density matrix, a mixed state, right? They don't know exactly what state you're picking. So psi1 really should be like, think of it this as a mixture of states from E1. This is a mixture of states from E2. If you just give one copy, there's maybe no process that can distinguish between them. But then if you give 2 copies of psi1 and psi2, then suddenly there is an algorithm to tell the difference. And we'll see a quick example of that. Does anyone can think off the top of your heads an example of such an example?
maybe like plus and 1 and minus and zero. I have no idea why, but I think it should work.
Yeah,
Okay.
0, 1, and plus minus?
exactly.
okay.
Yeah, so some combination of those. So let's say ensemble 1 is you just have either a random classical bit, or ensemble 2, you have a random plus or minus state. So if you give someone a random state from ensemble 1, the density matrix they see is just a maximum mixed state, I over 2. So one copy, the density matrix.
They don't see the density matrix. They only get a state. Yes.
Well, they get a state, but that's equivalent to getting a density matrix.
Can they like see the entire density matrix? Like it's a classical description of the state.
Oh, no, so they don't get the classical description of
I
density.
see. Okay.
It's just
Okay.
mathematically we say
Okay.
that the
Okay.
input to whatever algorithm to get is a density matrix. So the density matrix, like this, the density matrix, remember, is just describing anything they could possibly learn from a random state. So if we have one copy, with one copy of E1, this is I over 2. And then if you get one copy of this random state from this second ensemble, it's also I over 2. So there's no experiment that can distinguish between the two. But if you have two copies, then the density matrices look different, right? The density matrices in this case will be 1/2. You either get the 0, 0 state, or 1/2 plus the 1, 1 state. And that's getting two copies of a state from here. And in this case, you get this other density matrix, which is different. Like you can just calculate what the matrices are and you see that they're not the same thing. So there is a way to tell the difference. So more generally, that's why like it's important to have this, for any small number of copies, you still can't tell the difference. That's why this is non-trivial. So that's example. We observed in the classical case that this polynomial time restriction on D is necessary. That's also the case here. So again, like can someone see the reasoning? Like if you allow the distinguisher to have unlimited time, and let's even allow it to have unlimited number of copies of the state, then there is a way to distinguish. What's the procedure?
State homography.
State tomography, yeah. So imagine that the distinguisher got an infinite number of copies of psi k or theta, then it can just do tomography, get a classical description and say, hey, is this state the output of our generator or not? If we were picking a hard random state, then the probability that you get the output of the generator is going to be vanishingly small. But here you need computation assumptions.
But if it does not have an exponential number of copies?
If it doesn't have then you still can distinguish. Good question. So if you only have a polynomial number of copies, then let's see.
Your example, you couldn't, even with unbounded resources.
Yeah. The example you gave now, even if I could run like for things between 0, 1 and plus
The one copy case.
Yeah.
That's right. Yeah. So this is a good pseudorandom state generator for one copy. right? Because there's no distinguishing between the two. But then once you go to 2 copies, you can distinguish. And so the claim is if you have a generator, there's a number of copies that you can find that's polynomial. That once you get to that point, then there is some measurement you can make to distinguish between the
But here, if you had just one copy, you cannot distinguish even with exponential unbounded time.
Right, yeah. Basically, the number of copies T that you need to go out in order to ensure that you can distinguish, it's going to be related to the number of qubits that you have.
See, and it's a polynomial number.
It's a polynomial. Yeah. Basically, this is sort of jumping ahead, but you have T copies where where 2 to the n. So 2 to the n is the dimension of the subspace spanned by all the outputs of the generator, right? There's 2 to the n different vectors that the generator can output, right? Take their span. The span is going to be a 2n dimensional subspace. If this is less than the dimension of the symmetric subspace on m qubits, the T copies, then we have the kind of like the analogous notion. Like the output space is much smaller than the outputs of the generator is much smaller than the total output space. Then there is some way to distinguish between the two. Then there exists an inefficient distinguisher. All right, so again, we need some sort of computational restrictions on who's doing the distinguishing. There are also some complexity theoretic implications, meaning that, okay, so pseudorandom states haven't been looked at as much, but I think most people would believe they exist. But it's not so easy to show they do, because if you did, you wouldn't show P is not equal to NP, but something morally as difficult. So observation, existence of a PRS, if you could show it exists, then you separated the complexity class BQP, which is quantum polynomial time, from P space. This P space is the set of problems you can solve in polynomial space. We don't know that this is true. This is a very difficult problem. So yeah, if you can show pseudorandom states exist, then you would have this complexity theory implication.
Even for QMA, right?
We don't know that's true. Yeah. In fact, I think we even have like Oracle results saying that BQP could be equal to QMA, but pseudorandom states still exist. Maybe, not 100% sure if that's true, but okay, other observations. We've defined this notion, this quantum analog. How does it relate to the classical PRGs? If you can come up with a pseudorandom generator, then you can construct pseudorandom state generator. We'll show this in the second half of class. But the reverse is not necessarily true. Meaning that if someone says, hey, I've constructed a pseudorandom state generator, then it's not immediate that they must have used a pseudorandom generator inside. Right? This is kind of in contrast to what I was saying earlier. Like if you take any classical crypto system, somewhere inside they must have used a pseudorandom generator. That's not the case here. Right, this is the final observation that I'm going to make before we continue. Remember I talked about the stretch of a PRG? Like if you have a PRG that achieves just a little bit of stretch, you can make it as long as you want. That's not known to be true for pseudorandom states. Okay, so first, let's say someone, again, they say, hey, I've constructed a pseudorandom state generator for you. It stretches n bits to, I don't know, n+1 qubits, right? You say, oh, great, but I really wanted for my application, I wanted a pseudorandom state that was n² qubits. Can you make that for me? Then there's no black box way that we know of to boost the stretch. Again, this is unlike the classical case.
So the thing is, like when I thought of PRS, I thought that you would start with like a hard random set, but on a smaller number of qubits and not a random string. So if you do that, can you then like,
We don't know.
I see.
So you've all saying, well, here we kind of have a mismatch of types, right? The input is classical, but the output is quantum. What if we make the input quantum as well? That hasn't been explored yet, so something to think about.
Why do people believe PRS exists?
Because if you think PRGs exist,
I see.
Is there a sense of whether people think that it can be stretched? Like, is there some reason to think that it can't be or that it can be? Or is it really?
good. So in some sense, if you assume existence of PRGs, since we know these can be stretched as much as you want, then you can get PRS with as much stretch as you want.
Okay.
What I'm saying is there's no black box transformation. Like if you hand me a generic PRS, like I don't know if it came from a PRG or not, then I don't know of a way just by itself to amplify the length.
Okay.
And in fact, I suspect you might be able to show like there is no black box way of doing this, but that's just a suspicion. Okay, so that's stretching. But what's even more funny is that there's no known way to even shrink a pseudorandom state generator, which is like, this is really strange because in the classical case, first of all, like if I give you a uniformly random string on m bits, it's easy to give me a uniform randomness on m/2 bits. You just discard the second half, right? No problem. That's a trivial thing to do. But with a pseudorandom state generator, this is not the case. Like you can't just drop one qubit and also have a pseudorandom state generator. So somehow it's a very rigid object. Okay. And let's see why. Like, so this is the first thing we're going to try to prove. The claim is the output of a PRS if you have a PRS generator G is highly entangled. This sort of explains why, if you had, you got these m qubits as output, this is your pseudorandom state, right? All of the qubits are going to be entangled with each other. And if you just drop one, then what you get is you don't get a pure state anymore. And it's going to be actually distinguishable from a Haar random state. So let's prove this, and I have to first explain like how do we quantify what does it mean for something to be highly entangled? There's many different ways of measuring entanglement. In this case, we're just going to measure it via something known as the purity of a state. So so if we have m qubits here, we can say that it's highly entangled if, so here's the definition. So basically it's saying like, if we take any subset of our m qubits, maybe it's one subset here versus the other half, but it doesn't necessarily have to be contiguous. If you trace out, if you just discard these qubits, the remaining state that you have is going to be a very mixed state. Okay, it's not going to be close to a pure state. That's what this is roughly saying. Slice. So let's say you've divided the set of qubits into two sets, A and B. So A and B together form all m qubits, but we're just going to discard, let's say, the B subsystem. So we get a density matrix, rho A, that's formed by tracing out B. So you get some density matrix on the qubits indexed by A, and then the purity of rho A is defined to be, you take the trace of this density matrix, but you square it. Okay. And then you take the trace of that matrix. So what does this measure? If rho A were actually a pure state, then this quantity would be 1. The purity of rho A is going to be 1. On the other hand, like the other extreme, let's say that rho A is the maximally mixed state. So it's the identity over the dimension of A. Right? So let's say A was some number of qubits. The dimension of A is going to be 2 to that number of qubits. And the purity of this density matrix, well, you do the math, you square this, right? This is going to be identity squared divided by dimension squared. You take the trace of that, you get 1 over dimension of A, which is a very small amount. So that's sort of like the dynamic range of this purity measure. And it's just sort of measures how close, if you're very close to 1, then that tells you, at least across the separation of A and B qubits, they're not very entangled. But if your purity is very close to this small number, then it tells you that there's a large amount of entanglement going on. So purity of rho A being small implies psi is highly entangled across the AB subdivision.
The total purity would just be the minimum overall Partitions.
I guess if you want to combine it into one number, you can take the minimum. Here, we'll just talk about every possible cut. So I want to argue that the output of the pseudorandom state generator must have, across any cut, the purity must be small. To make this claim more precise. The randomly chosen seed K for any fixed cut AB of the qubits. The purity of row A. So I'll index this density matrix by K. So this density matrix is, you take size of K, you throw out the B qubits, and you just look at that reduced density matrix. We're going to look at the purity of this density matrix. This purity is going to be negligible. Right, so that would tell you that essentially if you pick, the output on average is going to, across any cut, is going to have this small. It's going to be highly entangled across any cut you want. So how do we prove this? Well, we say, suppose that weren't true. Suppose that if you ran the pseudorandom state generator, it output this state, but it actually there was some cut where the qubits weren't highly entangled. Then we can find an efficient distinguisher between the pseudorandom state generator and our random state. Then we show that there exists a efficient polynomial time distinguisher that distinguisher is not supposed to exist, right? So that would be distinguisher D that tells the difference between psi k and the Haar random state. Okay, the distinguisher is very simple. It takes in 2 copies. So it's going to take in 2 copies of a state. And it's going to first throw away the B qubits on both of these copies. So both of these have qubits that are indexed by AB. Right, so actually let me do it this way. So there's the A part here, the B part goes here, the A part and the B part of the second copy comes here, and then we do, okay, so we just completely ignore this B part. I'm just going to say we, think of it as we just trash it, and then we're going to perform something called the swap test on these 2 A components. So to do a swap test, we introduce another qubit. This qubit starts off in the plus state. And controlled on this qubit it's going to swap these two sets of qubits with each other. Right, so remember the plus state is this superposition between 0 and 1. If it's 0, then it doesn't do anything. If it's 1, then it's just going to swap those sets of qubits around. You perform a Hadamard on this control qubit, and then you measure. That is the output of our distinguisher. So this thing. And here's a claim. This will be, it might be a homework problem. So the claim is, well, what is the probability that this qubit measures to be 1?
Sorry, the extra bit used for the control is changing. There is a reason for it not to be that exactly.
Oh yeah, because basically this qubit, it will become entangled with these qubits when you do this control. So it won't necessarily be in the plus state. Yeah. So the claim is that the probability that the distinguisher gets 2 copies of psi, probability equals 1 is going to be an estimate of the purity up to some fudge factors. So it's going to be 1/2 plus 1/2 times the purity of rho A squared. You guys, this truck is not working. This circuit, it's a simple one, but it gives you an estimate of the purity of the reduced density matrices of these 2 copies. So, so here's the thing. So imagine that we were supposing for contradiction that there were this unentangled subsets of your pseudorandom output. You plug that in, you run it through, then this purity would be noticeably different from probability 1/2. Right, the probability of it being 1. On the other hand, if you put in a Haar random state, you do the calculations, a Haar random state is going to be completely entangled across any cut. So the probability that this distinguisher outputs 1 will be indistinguishable from 1/2. So this is your distinguisher. This is how you prove that PRS states must be valued. Okay, let's take a break. Let's come back at 2:10, 3:10.
What doesn't change? Like, yeah, so they're the same state. Yeah, so no matter if I swap or not, it's still like the same. Just trying to make.
Well, it's the same density matrix, but remember, density matrix is a probabilistic mixture. So there's a probability that they're not the same pure state.
Aren't the qubits A still the same one?
Yeah, that's what I was asking.
Yeah, so this part's a little counterintuitive. When you trace this out, you have mixtures here, right? Because they're density matrices. So think of it as essentially the state here and the state here are sampled independently. So actually with some high probability, if it's very mixed, they're not going to be the same state. So when you swap them or you don't swap them, that this qubit can tell the difference.
But we aren't measuring either of them, so they still are in the same ensemble. So how do we differentiate between them?
Well, they're the same ensemble, but okay, it's equivalent to the following process. So think of the input into the circuit as being two mixed states, right? But really, when we analyze the circuit, we have to talk about pure states. So how do you analyze the outcome of the circuit? You say, well, these mixed states are some probability distributions over pure states. So why don't I just sample from those distributions first? Then everything's pure. You have a pure state here, pure state, and then I analyze it. But when you sample from these two ensembles, you see, with high probability, you can get different pure states.
And then I account for the sample probability in the end.
In the end.
Okay, okay.
One by dimension A or the squared.
It's going to be 1 by dimension of A.
But like in the definition, it's trace of rho A squared.
Yeah, because you have to take the trace of the identity, which is one factor of dimension.
Why replicable such with a string and not hard state on a smaller number u bits? It would feel like maybe actually the latter would be perhaps easier to construct.
Yeah. It's a good question. We don't actually, somehow it just turned out to be easier to think about.
I see. Oh, okay.
It's a really good question. What happens if you start with a smaller volume? Like, I thought about it for a little bit, but I didn't make it after it.
Do you have your second?
Even then though, it's not clear that just like composition.
Sure. Sorry.
Even then, it's not clear that composition would give you stretch.
I mean, I guess if you had that, then composition would be sort of repeat.
Yeah, like in my head, some sort of a hybrid.
In a long time since
Type of argument should work, but maybe there's some quantum thing that makes it not work.
Yeah, I guess it depends on if you assume you have a family.
Mhm.
If you have a family, then sort of composition, you just say, well, you run it once, and run it on the bigger thing,
Yeah.
and run on the bigger thing.
Yeah.
But if you only have a fixed size of a
Okay.
generator, then
Then it's weird.
you know, leave the circuits up.
No, nowadays I usually make some stuff. Are you considering getting a suite or something?
If I may, one more question.
Yeah.
Are there like so in classical we have PRGs for like interpretation. Like that means quantum, like example exponential PRG for example.
Some way you can try with every other thing, but then
You mean like
also-
space bounded,
Yeah,
things
yeah,
like
yeah.
that, that's what you're asking?
Yeah. Space bounded.
You might go down a very long
Like
rabbit
against
hole.
adversaries that are weaker than
Yeah.
arbitrary polynomials.
Oh, you mean like unconditional?
Yeah.
That's a great question.
I actually,
That's, yeah, me too.
I'm not good at that. So you remember that in crypto, basically, nothing's known about this.
Because he's working on it. He said it's not in quantum, he's working on it in classical.
Be very natural.
Yeah.
Oh, I don't know, it's just like,
Algorithm.
I think if you like do all.
So we have to like let
What's that all?
turn to mathematicians and let them rule out impossible questions.
That's a nice, yeah, that's a nice.
Explore the structure, we have to show that this is not,
Considering
it is far from a
doing
random
no
set.
progress on trying to do
It's
something.
more structures
it's high
in
enough.
this set to help us determine whether it's something. Recommend this survey. Yeah, you can make it into a clique, that's also. That's what I have tried, but I don't know.
When what you're doing now is
It's a lost survey.
you're proving that PRG implies PRS. Is that post-quantum PRG?
Yes.
So the like standard PRG versus PRS are uncomparable. Like PRG, that's not post-quantum, it's just secure against classical.
Yeah, that one
adversaries.
is breakable. Breakable, it's probably breakable. Yeah, if you have like a PRG based on factoring or something.
Yeah, but no, but if I have PRG as a abstract primitive, that's like, that definition is incomparable to PRS.
You mean against classical adversaries?
Yes, PRG against classical adversaries versus PRS, the way you define it.
Oh,
It's not clear which primitive is strong, right?
I'm glad that I didn't see, I understand.
I mean, but it's incomparable because we know, like, if you assume that there is a, like a one-way function that's secured classically, but not secured quantumly, then we know of an attack.
I see.
I see, if you say it's specifically not secure quantumly, okay, I see, then it's definitely weaker.
Yeah.
And if it is secure quantumly, it's definitely strong.
Yeah. Okay, so continuing on. So the second half, I said, people believe pseudorandom states exist. Why do we believe that? Well, because assuming a pseudorandom generators, we can, which, most cryptographers and computer scientists believe they exist, then you can construct PRS. So let's see how to do that. But first, before I do that, I have to introduce another classical object because it makes our lives easier. This is something known as a pseudorandom function. Okay, so there's another acronym PRF, pseudorandom function. Here's the picture. It's another function. Let's call it capital F now, but it takes two inputs. So it takes in a key, right? This is still the seed, and it takes in another string X that we will maybe confusingly call the input, but this is the input X, and it outputs a single bit. So what's pseudo-random about this? Basically, okay, I'll write the definition and then we'll try to make heads or tails. So FKX is PRF. It's polytime computable, right, as usual. Be able to compute it in the forward direction quickly. And for all polytime distinguishers, so the distinguisher, it's not going to necessarily get the output of this function. So let me say what it's doing. So we're going to sample a seed at random. Okay. It's also called a key. So key and seed are the same thing. This algorithm D gets query access to this function. It doesn't know what K is. K is sort of sampled by someone else. But once that's sampled, then what is f sub k? It's a function of x only, where you take your PRF and you fix the first input to x. And then all you feed into it are these x's, right? So what this algorithm is doing is it's just choosing different x's to plug into this function. It's going to query it. D is a quantum algorithm, so it might make superposition queries, right? We talked about this query model before. So maybe it says, well, I'm going to query all of the inputs of f sub k in superposition, do some quantum computation. And at the end of the day, I'm going to output a 1 or a 0. All right, so it's going to try to figure out, am I getting access to this pseudorandom function? In a different experiment, this same algorithm gets access to a different function, but it's going to be a completely random function. So f is going to be a random function on m bits. Right, so this little f also gets in, it takes in x's, but it has nothing to do with this capital F. It's just a completely uniformly random function. So this capital F is a PRF if you choose K at random, you can't tell the difference between them.
It's been a while since I took a quick crypto class, but does it matter that D is polytime, or only the query complexity of D is yeah?
I defer to tolerance.
I mean, both of these notions make sense.
I see, but they're not known to be like equivalent
I
or
mean,
something.
usually you define D to be polynomial to time, not just number of queries.
I see.
Just polynomial. And it makes sense
To think about
to think about arbitrary.
I guess if it's if this F it has the code of F, then it actually is important for D to be polytime, right? Because otherwise it can like
Oh, I see.
it can just invert.
If it has the code of F, yeah. I mean, if it has the code of F, then clearly it's not. Then it has K. I guess you could obfuscate though. I don't know, right? It could be obfuscated.
Yeah, I guess, yeah, but we don't want to go there. Yeah. Okay.
But in the definition, it's black box access, like you wrote, Oracle access.
Okay, so classical stuff, right? But we're going to make use of this.
But this is not classical because D is not classical, right?
Good.
In your definition, right?
Right. So I'm thinking of F as being computable by a classical algorithm, but its security holds against all quantum adversaries. So this distinguisher D could be a quantum algorithm. So that's the only quantum part of it. Oh yeah, and then so here's why I'm introducing it. It turns out that PRGs are equivalent to PRFs. Equivalent in the sense that if you walk up to me with a PRG, I can do some complicated crypto magic that you learn about in Tall's class to construct a PRF and vice versa. Right, so they're equivalent objects crypto-wise. This is a theorem due to G, Liu, and Song in 2018. So in this paper, they introduced the notion of pseudorandom states. So it's like a brand new notion from a few years ago. And they also show that using PRFs, you can construct PRS. So in one word, they say that PRFs by PRS. So this is what we're going to do for the rest of today. We're going to show how this construction works. And the construction is actually quite simple. You say, all right, someone walks up to you with a PRF, this capital F. So we have F, it's this math. This is a PRS. We're going to use it to construct a quantum state. So here's how the generator G is going to work. This is our PRS generator. It says input an n-bit seed, K. And the first step is going to prepare the uniform superposition over all m-bit basis states. So we have 2 to the minus m over 2 superposition over x at x. So x is m bit strings, right? This is the same m as the second input to the PRF. So preparing the state is very easy. You just take m qubits all in the all zero state and you just apply Hadamard's to each qubit independently, right? Then you prepare this uniform superposition. Second step is we're going to compute this pseudorandom function, capital F sub k, the superposition. Right? And then you get the resulting state, which is this superposition but the phase in front of each basis state will depend on your pseudorandom function. Right? So in other words, whether it's plus or minus 1 here depends on whether the output of your pseudorandom function is 0 or 1. That's it. That's the PRS generator. So claim number 1, this G had better be efficiently computable. So G runs in polynomial time. Why is that? Well, the first step is pretty easy, right? You just do this all Hadamard's. And then when you compute F in superposition, you're going to rely on the fact that this capital F is also computable in polynomial time. So you just do that. Okay. So now all that we have to do is to show that these size of k's are indistinguishable from being R random. Right, and that's the interesting part. K's. Right, so for every key K, there's a different quantum state size of K. Okay, we're going to look at this ensemble of states. Is indistinguishable from R. Even given a polynomial number of copies of these states. So we're going to do that using the main trick in crypto, which is known as a hybrid argument. So right, we're going to say we're going to create 3 different scenarios. the first scenario is going to be one where the distinguisher is given the output of this generator, so it's given psi sub k's. The very last scenario is going to be a case where the distinguisher is given just hard random states. And then the middle scenario is going to be some interpolation between the two. So let me write we're going to talk about them in terms of experiments. So experiment A, which I'll call the real experiment. This is what's happening in real life in the sense that the distinguisher is getting these pseudorandom states. All right, so we're going to fix the distinguisher D and a number of copies T. So these are just thought experiments. They're not like they're just for the purposes of analysis. So we say in our heads, let's imagine that the first step in this experiment is we're going to sample a random key, a random seed. Second step is that we're going to compute the generator T times to get T copies of this state. The third step is we're going to take our distinguisher, which is some quantum algorithm, and we're going to plug in our T copies. And then the fourth step is whatever, this distinguisher outputs a 0 or a 1, and we just return this output. So this experiment also has an output. It outputs a 0 or a 1. All right, so that's experiment A. And I'm going to talk about the next experiment. This is experiment B. This is the hybrid experiment. Okay, so it's going to be, we're going to do the step slightly differently. We're going to sample a random function, little f, that maps m bits to 1 bit. This is not something that you can do efficiently, but that's okay. We're just doing this in our heads, right? We're just like, this is a thought experiment, right? This requires specifying 2 to the m different random bits. Imagine we did this in our head, then we can generate T copies of a different quantum state. Let's call it psi sub f. And it's going to be the uniform superposition. But now the phases come from this random function rather than the pseudo-random function. And then steps 3 and 4 are the same. You take these T copies of psi sub f, feed in the distinguisher, output whatever the distinguisher outputs. So we just tweet what state we're feeding into the distinguisher. And then finally, we have experiment C. Which is, in the first step, we're not going to sample a random function, but we're going to sample in our heads a classical description of a Haar random state. We're gonna sample this theta, R measure on m qubits. Again, this takes exponential time. That's okay. Now that we have this classical description, let's generate T quantum copies of it. So we're going to synthesize. And then steps 3 and 4 are the same. Take these T copies, put them into the distinguisher, and okay, so I defined these 3 experiments. And our goal is to argue that it's equivalent to arguing that the probability that experiment A outputs 1 is close to the probability that the very last experiment outputs 1. Right? So and we can do this, and we're going to use the middle experiment to help us bound this. So we can accomplish our goal by arguing we're going to show that the output of experiment A is going to be very close to the output of experiment B, and the output of experiment B is going to be very close to the output of experiment C. So that's why we call this a hybrid argument. We use this experiment B to kind of link the 2 together.
Very close in the eyes of a polynomial time distinguisher.
Yeah. Okay, so let's think about this first comparison. We have these A and B. So what's the difference? In one case, these states psi k, their phases are generated by a pseudorandom function. And in the second case, the phases are generated by a truly random function. Why do we know that experiment A and experiment B must be very similar?
Because of the PRF, right? Like, yeah. If they were not similar, I think I can construct 2 like step 2 in both of these in my head, and then I just run a distinguisher that I have for the PRF, and I know the.
Right. Exactly. So this just essentially follows from the definition of pseudorandom function. As Yuval was saying, like suppose they're like for some reason the output distributions of this were different, then I could use the same D to tell apart between a pseudorandom function and a random function. Right? I would just run these 2 experiments. But by the PRF says you're not able to tell the difference.
But is it an issue that we said that we can't actually run this experiment because it would take, you said that this experiment would take exponential time to
Good. Okay.
set
So
up?
yeah, good, very good point. So what I said wasn't totally correct because this step 1, this is not part of the distinguisher because it takes too long. So really what I'm saying is that the distinguishing,
Like step 1 was done, but not by me, right? Like someone else came, did step 1, and then gave me Oracle access to the result. So it was done, but just not by me. So I'm still running in polynomial time.
So if you remember from the definition of PRF is like this D gets access to either the F sub K or the little f.
Oh, and this is.
So we're imagining someone picked for us the F little f already or the F sub K. Regardless of which, we're going to do the same thing. We're just going to compute this state and T copies of it. So, and that part, this part is polynomial time. So yeah, good question. Good. Okay, so now, that part, it follows from the PRF, and now we just have to argue this last step that that these states psi sub f with truly random phases is indistinguishable from Haar, and that's where we just have to roll our sleeves up and do a calculation and show that really that these are essentially Haar random states. And so that's what we're going to do for the rest of the class.
Saying that your experiment 3 is actually generating a PRF, like a quantum analog of, like the Haar state is a quantum analog of a PRF. No?
Quantum analog, it's an analog of a random function.
Of a random function, right?
For only a polynomial number of copies, though. So this indistinguishability holds only when T is poly n. So, and we'll see this in the calculation. So just, if all this experiment stuff was kind of confusing, let's just bring it back down. And now we're just trying to argue that T copies of, and I'm just going to drop the normalization for now. Even forget this F. I'm going to write it as alpha sub x. So alpha sub x is going to be a uniformly random plus or minus 1 value. Alpha sub x or IID plus minus 1. We want to argue that this state is close to T copies of our random state. And what's interesting is at this stage, we no longer care about polynomial time or exponential time. These states are actually like information theoretically indistinguishable. So yet another way of saying it is we're like in mathematical terms, we're trying to bound the trace distance between two mixed states. So in one case, we're going to pick these alpha x's uniformly at random. And then we have these size. The difference between this and our Haar random theta remember, the trace distance is just a measure of distance between mixed states. We're going to argue that this is T squared over 2 to the m. So x is, remember, m qubits. All right, so, and T is going to be some polynomial. So this quantity is going to be vanishingly small, right? Okay. And first thing, does anyone remember what this thing is? Right, we're taking an average over T copies of a Haar random state. We had a formula for this. Been a while. There's some mathematical keywords.
It's an integral over the Haar machine.
it's an integral of the Haar measure, and we have a closed form expression for it. You know what it is?
Projection on the symmetric.
Yeah, symmetric subspace. So that's from, I don't know, that was from a while ago. But yeah, it's that object is this projector onto the symmetric subspace scaled by some normalization factor. So let's recall that. So this here, it looks like some complicated integral, but we learned that this is, as a matrix, this is projector matrix onto T copies of the symmetric subspace, where each copy is capital M dimensional. Capital M is just this 2 to the little m, and we're going to divide it by the trace of this projector. So for simplicity, I'll just put pi, right? We'll leave all these superscripts and subscripts off. And we had a formula for what the trace of this projector is. It's the dimension of the subspace. Remember, it was this binomial coefficient. So that's going to be very useful very soon. But good. So we can just plug that in, right? This is just this normalized projector. And okay, good. So let's return to this psi and take a closer look at it. So this is 2 to the minus m over 2 summation over alpha x. These alpha x's are chosen at random. And we're going to take t copies of it. So if we tensor this up t times, we get a whole bunch of indices. So we're going to get normalization is 2 to the minus mt over 2, right? So this is just raised to the power t. And then we have indices x1 up to xt. Each of these are themselves n bit strings. We're going to sum over all of them. This scary looking state. So in total, this is n times t bits. So I'm going to look at a closely related state. I'm going to define a pure state sigma. This state is also going to be on m times t qubits. We're going to keep the normalization the same. But we're just going to drop terms from this sum. Sum over the x1 up to xt that are distinct. Okay, so each of these are m-bit strings. And if there's any term where any pair of these are the same, we're just going to drop them. So we're going to keep them all the same. All the coefficients are going to be the same. So, so this is some new state. And the claim is that these states are not too far from each other. So this is if you look at the distance between these two vectors, so this is where we take t copies of psi minus this new state. in Euclidean norm, this is not very far. So this is an exercise, but really this is just a probability exercise. It's saying, suppose you draw T strings, each of n bits long, what's the probability that any one of them collide? And if your T is not too large, then the probability is actually going to be very, very small. Right, so that's what this calculation is expressing. Okay. So now that we know that these two are close, we're just going to think about this sigma because it makes our lives easier. We want to argue that now our goal is to say that this expectation over the alphas, sigma, is close to our symmetric subspace projector. Normalized. Okay, so this is what we want to show is small, because if we do this, then we're done. And we just have to expand out what this thing is. So this is going to be kind of a mess in the beginning, but we'll simplify. So we'll just open up the brackets. So this is expectation over the alphas. And right, we just take this and then we take its Hermitian conjugate and multiply everything out. We get 2 to the minus m times t as a prefactor. And then we're going to have a very large summation. So we have x1 up to xt, y1 up to yt. And again, we're going to keep that the x's are all distinct, the y's are all distinct. Pick up all these alphas. Okay. So this is the density matrix. It's a lot of terms. All right, but here's the thing we're going to do. So this ket and bra here, this is a matrix. These alphas are just numbers. So we're going to bring in the expectation over the alpha to calculate what the expected value of these alphas are. So we're interested in, suppose you fix x1 up to xt, y1 up to yt that are all distinct. We want to know what this number looks like. This is just a number, right? Because we're just averaging over these alphas. And the claim is that this has a very simple closed form expression. So any guesses or any thoughts on what this number simplifies to be?
Alphas are taken from where again?
They're just uniform for, yeah, each alpha x is completely independent of all the others.
So one, if and only if the two tuples are the same.
Yes. And if it's not one, then it's
0.
good. Exactly. So this is numbers either 1 or 0. So if x1 up to xt, remember these are all distinct. X1 up to xt is a permutation of to yt. And this expectation of the alphas is equal to 1. Why is that? Because you match up the alphas, you just pair them up, right? And since they're plus or minus 1, they square to 1. So this is just going to be 1. Otherwise, the expectation of all the alphas is equal to 0. And this is because if they weren't permutations, then at least one of these strings are going to be different from all the other ones, right? But then when you take the expectation of that, it's going to be plus or minus 1 with equal probability. The average is 0. It cancels out. Okay, so we have a nice expression for this. That means we can just continue to drop terms. This density matrix is just going to be 2 to the minus mt, and you just sum over all the x1 up to xt's, and you're going to sum over all possible permutations of these strings. So I'm going to call that I and st. St is the set of permutations. And you just have some permutation of these x's. Make sense? Now we're almost there. Okay, so now that thing is going to be equal to, so here you can do the algebra on your own, but I claim it's equal to 2 to the minus mt times some matrix A times the summation over all permutations of this permutation operator. Okay, what's A? A is just going to be the summation over distinct. This is kind of messy, but you're just summing over all the x1 up to xt's that are distinct. And you're looking at this, it's essentially a diagonal matrix, right? And you're just multiplying by the summation over all permutations, where you just shuffle around these strings according to the permutation. Right. So I'm just simplifying this. It also turns out that it does, it was kind of arbitrary that I put the permutation on the right-hand side. It's also the same if I put the permutations on the left-hand side. So it's also equal to this. All right. Okay. Does anyone remember what the summation over these permutation operators was? This was, I think, in your homework. This is also another way of writing the symmetric subspace projection. So that's another fact that we'll use. So it's not exactly projection, it's going to be t factorial times a projection. So this projector pi is equal to this summation over these permutation operators divided by t factorial. Okay. And right, so we have these 3 different ways of writing it. You have pi on the left, pi on the right. You can also just put pi on both sides. Right. So now it starts to feel like we're actually getting closer to our goal, right? So we're trying to show that this object, which is through all these manipulations, that's the original density matrix of the sigma sigma. The sigma sigma density matrix is this object, one and the same. And we're trying to argue that it's close to pi divided by trace of pi. So we're almost done. I gotta show that is 2 to the minus mt times t factorial pi a pi minus pi divided by trace of pi is this small amount. And now, like, it seems very promising, right? Because now we're just comparing pi's with each other. And, okay, a couple minutes left, that's all I need. So, long story short, if you sort of write out what this trace distance should be, you can break it up into 2 different estimates that you want to make. One is you say, well, let's estimate one of the terms is where we want to we want to keep this normalization the same. So we have 2 to the mt times t factorial times pi a pi minus pi. Okay, so here we're basically saying, well, let's pretend trace of 1 divided by trace of pi is close to this, which it will be. And then we say, well, actually, how much was that difference? And that's going to be 2 to the minus mt times t factorial minus 1 divided by, and we had this formula for trace of pi, which is m plus 2 to the m plus t minus 1, choose t. Okay, so a homework exercise is that these 2 numbers are very, very close. How close? Going to be this close, right? You just sort of expand out the binomial coefficients, do some basic algebra, and then you see these 2 numbers are very close. And the claim is that this quantity is also, it reduces actually to the same calculation. I'm not going to go through it because it's just a few lines of like arithmetic, but we're basically you just get this. That's what we wanted to show. We showed that this experiment B is close to experiment C, and that kind of finishes everything. Next week, we'll cover applications of pseudorandom states.
Yeah.